let me.
Okay, and so the talk by Marco is entitled Success or Draw, a strategy allowing repeat until success in quantum computation. Mm, okay, so I think we can start. The floor is yours.
Okay, well, thank you for the introduction, and also I would like to thank all the organizers. Like, I think it's been very nice. The program is very good, and everything is working well. Thanks everyone for attending. So this work. So we finished this year, kind of, when I was in University of Tokyo in Japan. So with my friends and collaborators like Tosa, Akito Soeda, and Mio Murao. And hopefully, I think so. I like this work because, well, I think it's this kind of thing that the main message is simple, although there are some technicalities in the proofs. But I hope that in the end of the talk, you agree that the main message is simple and everyone can understand. So let's see. So the motivation for this project, like, is imagine that you have a unitary operation, so a quantum gate, if you want, that we want to do like a quantum circuit to transform it to another unitary operator, f of u. So f would be, in this case, just a function. Then if you want to transform like unitary operation, the dimensional ones, to unitary operation. So what I have in mind is something like this. So like this block, where here you can plug like an arbitrary quantum state and something will go out here. And by this part here, where u is plugged, I want to imagine this as something that you can plug and unplug any unitary operation. So this part in white, sometimes people imagine this as like an encoder and decoder. So this would be like fixed quantum channels, so fixed objects. Then like this chunk, this object here, mm, here, and now there's inside, it's something that is fixed. And then I give it to you. You can plug any unitary you want, and what comes out will be another unitary, like transformation on you. So we're looking for this kind of like problems. And well, I think it's good always to have an example. And for this, my favorite example is something what's related with unitary complex conjugation. So here you can understand this is a quantum circle. This U2 here just stands for like qubits. So this is a quantum circle with qubits. And this star stands for complex conjugation in the computational basis. So the way you should understand this, that for any quantum state psi that you plug here, so the quantum state is going to evolve, right? So here basically you apply sigma y, you apply sigma 2, then you apply sigma y, and it so in psi. And then what you have is actually the complex conjugation applied in psi, and this works for every psi. Well, there's actually a small catch here that this must hold true up to a global phase, right? Because pure states, like we cannot tell the difference up to a global phase. So basically this identity here holds up to a global phase like it should be. So this is an example of like a quantum circuit that for any qubit unitary operation we plug in, what you have it out, it's the complex conjugation. Nice. So, well, it turns out that this example here, although it's very simple and beautiful, things are usually not like this. So in this example here, like if you pay attention, I didn't exploit, for example, this potential auxiliary system here. So I didn't enlarge the space. And also it's deterministic and exact. It always works. But in general, like it makes sense to consider a bit scenarios that are a bit more general. Right? These encoders here, they can enlarge the space and use some auxiliary parts. Here, like to have a kind of decoder. And it also makes sense to consider probabilistic schemes because the deterministic requirement is actually quite strong. So we can imagine something that with some probability you have like success, and then you implement what you want. With some probability you fail. And when you fail, well, you don't care, like that's failure. So basically we look for things that you transform like unitary operations into like some P, where this P stands for the probability of success. And well, just to be a bit more concrete, by success or failure, what I have in mind is that in principle, we can do a quantum measurement here And this quantum measurement, we have like two outcomes. One outcome means like success, like good, and the other one failure. Or in principle, it can have many, and then we just group the bad ones as a single failure. So this is the kind of problem that we are interested in. So we want to understand this kind of things. And it's important to say that we look for things that are universal. So this universal like paradigm, basically it means that here I can plug any unitary U. It doesn't work only for, or here I'm fixing the dimension, like D, for example, qubits, and here I can plug any qubit unitary. It doesn't, you don't need to know any like additional information. So it works for unknown unitaries. And we also require things to be probabilistic. Well, we accept it probabilistic, but it should be exact. So when it works perfectly. Here, like it's interesting like to say as well, then I don't know if it's obvious, but if the probability of success is close to 1 somehow, then you can also do a good deterministic non-exact version, right? Because you just ignore your outcome of success or failure, right? So if you have something that is probabilistically good, like success is close to 1, you also have a deterministic one that is good for many notions of like fidelity, these kind of things. So here in this talk, I'll focus on this probabilistic exact. And well, this thing that we know when we fail, right? This people sometimes refer this probabilistic heralded scenario. Great. So now the question is like, you have like a desired function f that you want to implement, like this complex conjugation, unitary inverse, or anything you have in mind. And imagine then you do have this quantum circuit, so you know how to transform u to f of u with some probability that in principle may even depend on you. You have that in your hands. But imagine that this p, u, I don't know, imagine that it's small, or you just want to increase it. You want to make closer to 1. How do you do it? Like, how can you increase? How can you boost this success probability? And I would say that that's the main question that will lead our results. Okay. So when you are in a situation like this, there is a trick, I'll say standard trick that people use like in, well, math in several branches. That is this repeat until success. And well, this is not like a quantum coach thing that you should repeat until success. I hope I can make sense out of it. Let's get like a very simple example. Imagine that you have this coin here, like this old Roman coin that I've chosen, like, and you're going to do like a head or tails. And say, if you say that P is the probability of getting heads, well, P doesn't need to be 1/2, especially if this coin, probably it's quite biased, no? But let's say that P, the probability of getting heads in a single toss, like you flip the coin. And then imagine your goal is to get heads. You like heads for some reason, like, I don't know, you like this side here. Like, and then if you flip and you get tails, how do you increase your probability of getting heads? Well, you just keep flipping, right? And actually, the probability of getting heads at least once with n flips, it's very easy to evaluate, right? So basically this 1 minus p is the probability of getting tails. That means like for us, kind of like failure. So, and then since these events are independent, well, we believe it to be, right? So the probability of success of getting like at least once would be n, 1 minus the probability of failure to the power of n. And what is nice is that, well, this number here, like, well, if p is not 0 and not 1, this is going to be a number between 0 and 1 to the power of n, right? So exponential decay that we have here. Like, so the probability of success is going to approach 1 exponentially. What is great? So this is what I mean by repeat until success. So now let's go back to our problem. So imagine that you have this quantum circuit here. So you can transform u to f of u with some probability of success, some probability of failure. Oh, that's great. If you have this circuit, you just do repeat until success and somehow problem solved, right? So basically anything that you can do, any transformation that you can do for unitaries, you can make a probability of success approaching 1 exponentially. But well, actually, what I said is not really right, because it depends on how you fail. Right? So if you try to follow this quantum circuit here, let's say you plug here a quantum state, and then it goes, it evolves, you apply the unitary, it comes back. here there's a quantum measurement that decides success or failure. If you get success, well, great, perfect, we're done. But if we fail, actually your quantum state will go under an evolution that you don't really know, right? So it depends on how you fail. Like actually, if your failure is very bad, you don't want to keep interact this protocol. And so we cannot implement this repeat until success if you fail in a way that you don't understand. And basically what we need is this success or draw. So now what do I mean by success or draw? So let's try to be a bit more precise here. It's basically a quantum circuit then with some probability you have success and then great. And when you fail, actually it's not really a failure, it's a draw. So basically you implement, this stands for this identity gate. Well, you don't do anything. And if we have this success of draw, well, protocol, if you have this circuit, then we're good, right? So if you want to implement something, you input your quantum state, and you go, you follow. If you have success, you're good, you're done, good to go. Or if you have a draw, refeed this state and keep interacting. Then we can do similar to the coin tossing, and the probability of success approaches 1 exponentially. So now question is like, can such a thing exist? Like, can you do this success or draw? Like, and to be honest, first time I thought about this problem, my feeling is then I would say no, this thing cannot exist, right? Because we have this, or what I put here, this quantum bad guys like this, no cloning and measurement disturbance. For example, if we can clone, our task would have been trivial, right? You get this input state here, you clone, you get many copies, and then like when you fail, you just discard, and this is equivalent, that's draw, then you keep trying. But we know that cloning is forbidden. And also, in order to the success of draw, here you have a quantum measurement, right? And when you fail quantum measurement, usually things you cannot go back. Like, well, a simple example, imagine that you have a qubit state that you don't know. So someone comes with a state psi, and then you perform a measurement in the computational basis. So then you may have the outcome 0, 1, and that would be like your output state. If you perform a quantum measurement, you got the result, let's say 0, the computational basis. So you perform a sigma z measurement, 0. Then your state is now going to be described by cat 0. And what about cat psi? It's over. It's over. You cannot go back. If you didn't know before, you never know it. So can we do such success or draw? So I will now first show one example, then kind of like motivate our research a bit. And this may clarify things. So this example that I'll show is based on a previous work that we had, where this function f of u, it's actually the inverse of the unitary. It's -1. So our goal is to design a quantum circuit such that for any unitary u you plug, you have the inverse. In this example here, like I'm going to talk only about qubits. So let's try to make sense out of this circuit here. So our first quantum state psi, it's going to be a qubit that comes here. And this quantum circuit, like this black boxes here, they stand for this other part, this encoder and decoder. But now I'm revealing what I have. What is the encoder? So this cat psi, cat phi plus here is just the maximally entangled state. So I'm going to prepare a maximally entangled state and do this. This measurement is going to be the Bell measurement. So let's try to understand this chunk of the circuit. We saw it before. So this is the complex conjugation. And also maybe you have seen something very similar to that. Well, this is essentially this state teleportation or gate teleportation, if you want. But with this nice property of the maximally entangled state, that basically you have things like this, right? That you can change side of the operation you're applying by getting a transpose. I hope this can kind of convince you that basically when this Bell measurement has the outcome related to phi plus, what will come out here is the unitary inverse. If you didn't follow, like, don't worry so much. But basically this Bell measurement here, like we parameterize on this, well, I and j, such that we have like 4 different outcomes. And the 0, 0 corresponds to the case where you get the phi plus state. And then, well, it's a simple calculation that you can just follow and check yourself at some point. Like, or you get any quantum state psi that you plug here, what you have, like in the case of 0, 0, you have the inverse. And in case of failure, things are different than 0, 0. Well, this is the general case, right? So you can even see that this J and I here, they mean like powers. So if this is 0, you get inverse. If not, and now we face like somehow the problem, like, can we do a success or draw? Usually, well, if we have success, it's great. If we fail, this is failure, right? It's not a draw because we are going to perform these operations here. Like, and since this unitary U is unknown, like it's universal, like we cannot invert this sequence of operations. But well, U is unknown, true, but actually we can invert, right? So in this case, it's quite simple because since this is the inverse of U, or the inverse of U inverse is simply U. So here we cancel each other. And well, since this measurement is heralded, we know the outcome of I and J. So basically, I hope that I have convinced you that for this particular problem, if we have an extra call of U, so here we use the unitary U once. If we have failure, we make another use. So with 2 calls, we can do the successor draw. So well, for qubits, unitary inversion, 2 calls, successor draw, it's possible. So what seemed to be crazy and impossible, it's actually possible. But well, probably what you're thinking, right? Well, come on, like qubit and unitary inversion, and this was so particular, right? So that's the reason why we can invert, we can reset, because the unitary inversion, like how about general functions? And if you could survive up to here, now you can get our main result. So our main result is perhaps surprisingly, at least for me, successor draw is always possible. You can always do such a thing. It's not a particular instance of qubits or unitary inversion. And moreover, like the number of calls that you need is at most D calls. So it means for our qubit case, where D equals 2, D here stands for dimension. For our qubit case, our scheme is somehow optimal because with 2 users, we could, well, this is a constructive example of successor draw. So I'll be a bit more precise on the statement of the theorem here and try to be more precise now in each slide. Basically, what we have is, if you construct this, if you come to me, hey, Marco, I have this quantum circuit, so I know this encoder, I know this decoder, such that I implement f of u with some probability of success p, and with some failure like 1 minus p, then I'm going to tell you how to write another circuit that does a successor draw version. And moreover, the circuit, we have this structure here, this nice structure line that has that too. So if you tell me how you do this, I will tell you how you do this. And if your probability of success is p, and we can even say p of u, that may actually depend on you, well, the successor draw version will actually have some epsilon p of u, where this epsilon is some number that is strictly greater than 0. So, well, somehow this is the same thing, but written with equations, not drawing line. But the statement is, if there exists a quantum circuit such that this transformation is possible, well, there is a depth 2 successor draw circuit such that this is possible. And well, I don't want to talk about the proofs because I don't see the point, but I'll just tell a bit like what are the methods behind. So we make like use of this formalism that sometimes referred as quantum combs or this super channel, super instruments, where we exploit a lot this Choi-Yamiukovsky isomorphism. And a lot of this was developed like in this work. Well, there are also many others like, and well, I don't expect everyone to understand this equation, but basically like this S target would be like the instrument, super instrument element corresponding to success. So if this is given and then you have a failure, and then, well, you can formalize everything in this nice Choi representation. And this is say like this success target plus failure should be like a C, a quantum comb. And then what we do, we seek for this probabilistic quantum circuit such that like, well, this funny thing stands for the link product, such that when you apply the operation on like k copies, you have a probability of success times epsilon, but instead of failure, we want this n of neutralizing, basically. And then in the techniques, like we kind of try to understand one method, something that is neutralizing have to respect, and we play a bit, we try to find a nice Pauli decomposition. Well, yes, this is just to give like a small feeling like the techniques we do, but I don't see the point in this short talk. But, well, probably what you have in mind, so this is the theorem, nice, but what about this epsilon that I mentioned, right? The PU and epsilon. And well, I have to be fair, this epsilon is quite bad. We don't, and very hard to evaluate because in our techniques, we have a bound that is not so good. What I can tell you is this epsilon is something like a d to the power of d squared, probably. So, well, if you have a probability success, for example, in this example that I mentioned is 1/4. So 1/4 times this epsilon is quite small. So, okay, it's a proof of principle. And of course, it grows exponentially. But then we have something good for you because usually you don't want to implement like a totally arbitrary function f. You know what you want to implement. So if the desired function is given, for example, the inverse or any other thing you want, this is given, and the number of uses is fixed, you say, okay, I want to use k times. For example, you can fix d as a dimension line. Finding this optimal success or draw circuit, like optimizing this probability of success, can be phrased in terms of the semi-definite programming. And this is very nice, right? Probably if you have worked with that before, like you can go to the computer, like and get many interesting things. Well, this is a hint on how you rephrase the problem in terms of semi-definite programming. I think it's a kind of technicality, just you can trust me for now that this is possible. And well, actually we went to the computer line. There are many nice packages for solving this semi-definite programming optimization problems, right? And then we went to the computer to see what happens, like for the qubit unitary inverse. So before I had present you a protocol that had a probability of success 1/4, and actually the computer is a bit more, they're quite clever. They have a success probability of 1/3 with 2 uses. So this tells that epsilon that I mentioned before, I said it's small, but it can be greater than 1, right? Because in the inversion, the probability of success was 1/4, and then 1/4 times the best epsilon you can find, it's actually 1/3. So, well, epsilon in this for this particular case, 3/4. So although what we have, the general construction is bad, if you have a desired function f in mind, things can go very well, actually. So I hope I can summarize things. So I'll say that repeat until success, it's a natural method to ensure success, right? If you do like something and fail, like keep trying. But of course, for this to work, you don't want success or failure, like, because if depending on how you fail, you don't want to keep trying, right? So, but if you do a success or draw, okay, if you win, you win. If you don't win, it's a draw. Come on, you try again, you try again. And success or draw is always possible. Where here by always, I mean like if you can do something with some probability PU, then by having like D calls, like D uses, you have a quantum circuit of depth 2. So it's kind of simple, such that the probability of success is going to be this epsilon times PU. We saw that this epsilon may be small in the general construction, but for every particular instance, we know how to optimize this epsilon. Well, that's the main result. We require D uses, circuit of length 2. In particular cases, may be analyzed with semi-definite programming. So I say, like, just to finish, like for the future somehow, like here, I have told you about a kind of like proof of principle, saying that it's always possible. And we also discussed this fine analysis for like desired functions, but we don't have like a friendly intermediate result. I mean, like, I didn't say the proof is constructive, so we know how to find these circuits, but it's not friendly in the sense that this epsilon, what we have is quite small, like, so it would be nice to improve a little bit, like to have like more friendly intermediate, like we can do like fully general, the probability is quite bad. Semi-definite programming with the computer, like it's perfect, the best you can get, but something in the middle, it's still missing. In particular, like good bounds for this epsilon, it would be nice, like the one we have, it's clearly an overshoot. And something I didn't mention, like if we start with more than a single call of the gate U, so like problems like this, for example, what you have, it's this kind of situation. So you start like this potential encoder and decoder, and now here you have the successor draw. So in the example like I discussed, like it's you give me a way to transform the unitary with a single call, and I tell you a way to transform with D calls. But and if you, how about if you start with two? So this is something that we still want to analyze. And well, the last thing I'd say, it would be nice to see a kind of a concrete application. Like for me, that's already applied. I don't know. It tells you how to implement any function f, but it would be nice to see like which functions f people want to implement and why, like, and how would that go like in practice. So for today, that's it.
Thank you
you.
very much.